Welcome to this session on solving the problem binary tree Inorder Traversal. In this video, we'll break down the process of traversing a binary tree in a specific order: left subtree, root, and then the right subtree. Whether you're preparing for coding interviews or just brushing up on your data structure skills, this problem is a great example to practice. Let's get started. In this problem, you are given the root of a binary tree, and your task is to return the Inorder Traversal of the tree's nodes values. Inorder Traversal follows a specific sequence. First, you visit all the nodes in the left subtree, then the root node, and finally, the nodes in the right subtree. You can solve this problem using either iterative or recursive approaches. The input consists of a binary tree node, which is the root of the tree. Each node has a value, a reference to its left child, and a reference to its right child. If a node has no left or right child, those references will be null. The output of the function will be a list of integers representing the values of the nodes visited in Inorder sequence. The output for this problem is a list of integers that represent the Inorder traversal of the binary tree. Let's take a look at an example. Suppose the input root is represented as 1, null, 2, 3. The tree structure looks like this. The root node has a value of 1, with no left child, and a right child with the value 2. The node with value 2 has a left child with the value 3. The expected output for the Inorder traversal of this tree is 1, 3, 2. To understand the output, let's break down the traversal step by step. Starting at the root node with value 1, we first attempt to traverse the left subtree, but there is no left child. So, we visit the root node itself and add 1 to the result. Next, we move to the right child of 1, which is the node with the value 2. Before visiting 2, we traverse its left subtree, where we find the node with value 3. We add 3 to the result. Finally, we visit the node 2 and add it to the result. This gives us the final Inorder traversal, 1, 3, 2. Another example is when the input root is an empty tree, represented as. In this case, there are no nodes to traverse, so the output is simply an empty list. For an empty tree, the traversal is straightforward since there are no nodes. The result is an empty list. Now, consider the case where the binary tree consists of only a single node. For example, if the input root is 1, the tree structure contains just one node with the value 1. Since there are no left or right children, the Inorder traversal simply visits the root node and adds its value to the result. The output, in this case, is 1. This demonstrates how the traversal works for the simplest tree structures, whether they are empty or consist of just one node. The problem comes with a few constraints and edge cases to keep in mind. First, the number of nodes in the tree can range from 0 to 10⁻⁴, so the solution must handle large trees efficiently. The value of each node lies between -100 and 100, meaning the solution must correctly process negative values. Edge cases to consider include an empty tree, where the output should be an empty list, and a single node tree, where the output is a list containing just the root's value. Additionally, you should handle trees that only have left or right subtrees, as well as very large trees with up to 10⁻⁴ nodes. Ensuring your solution is robust enough to handle these scenarios is key to solving the problem successfully. To solve the problem of binary tree Inorder traversal, we need to visit the nodes of the tree in a specific order. First the left subtree, then the root, and finally the right subtree. One intuitive way to achieve this is through the recursive approach. Since the traversal order directly mirrors the sequence of recursive function calls, we can define a helper function that takes a node as input. For each node, we first call the function recursively on the left child, then we process the root by appending its value to the result, and finally, we call the function on the right child. This method is simple and elegant, with a time complexity of O(n), because every node is visited once, and a space complexity of O(h), where h is the height of the tree. For balanced trees, this space complexity is O log n, but for skewed trees, it can reach O(n). While the recursive approach is natural and easy to implement, its reliance on the call stack can lead to stack overflow for trees with significant depth, such as highly unbalanced trees. Another way to perform an Inorder traversal is through the iterative approach using a stack. This method mimics the behavior of recursion by explicitly managing the traversal order with a stack. Starting at the root, we push all left nodes onto the stack until we reach the leftmost node. Then, we process the top node from the stack and move to its right child. This approach ensures that nodes are processed in the correct inorder sequence. Like the recursive method, the time complexity is O(n), because each node is visited once, and the space complexity is O(h), or h is the height of the tree, as the stack stores the path from the root to the current node. The iterative approach avoids recursion, making it safer for deep trees, though it introduces slightly more complex logic. Another option is the Morris traversal, which eliminates the need for extra space by modifying the tree temporarily using threaded binary trees. Here, if a node has a left child, we find its inorder predecessor, create a temporary link back to the current node, and proceed. If the link already exists, we remove it and process the node. This method has a time complexity of O(n) and a space complexity of O(1). While it is space efficient and avoids recursion or stacks, it temporarily alters the tree structure, which may not always be acceptable. For this problem, the iterative approach using a stack has been chosen as the strategy. While the recursive method is intuitive and elegant, it poses a risk of stack overflow in cases of deep or highly unbalanced trees. Morris traversal, on the other hand, is an excellent space-efficient alternative, but it modifies the tree structure temporarily, which may not align with the requirements in all scenarios. The iterative approach strikes a balance between these trade-offs. It avoids the risks associated with recursion, maintains the natural traversal order, and does not alter the tree. Additionally, it is robust and widely applicable, making it a practical choice for most situations. Key observations include the fact that recursion aligns naturally with the inorder traversal structure, while iterative methods provide a safer alternative to recursion. Morris traversal, despite its optimal space usage, introduces an intrusive step of modifying the tree. By selecting the iterative stack-based approach, we achieve a combination of efficiency, reliability, and simplicity, making it an effective solution for this problem. First, we have the base case. If the current node is null, meaning we've reached the end of a subtree, we simply return and stop further traversal in that direction. In this problem, we are tasked with performing an inorder traversal of a binary tree, which means visiting the nodes in the following sequence: first, the left subtree, then the root node, and finally the right subtree. The goal is to return the sequence of node values as they are visited in this specific order. To solve this, we will explore a recursive approach that uses the call stack to simulate this traversal process. The algorithm breaks down into 3 key steps. Second, for any given node, we recursively traverse the left subtree, visit the current node and add its value to our result, and then move on to recursively traverse the right subtree. This ensures we follow the left root right order at every step. The traversal terminates once all nodes have been visited, leaving us with the desired sequence of values in the result list. Once the recursion completes, the result list contains the sequence of node values in the correct inorder traversal order. To better understand how this works, let's look at the pseudocode. We define a function, Inorder Traversal, which initializes an empty result list. Inside this function, we define a helper function, traverse, that takes a node as its argument. If the node is null, we return immediately, as there's nothing to process. Otherwise, we first call traverse on the left child of the node, then add the node's value to the result list, and finally call traverse on the right child. After defining this helper function, we call it on the root node to kick off the traversal process. Once all recursive calls are complete, we return the result list. This approach works so well because binary trees have a naturally recursive structure. Each node's left and right children are themselves binary trees, making recursion an intuitive way to navigate through the tree. The recursive approach leverages the call stack to keep track of parent nodes as we traverse deeper into the tree. This allows us to backtrack and continue the traversal without needing an explicit stack data structure. Throughout the process, we maintain a result list to store the values of nodes in the correct inorder sequence, which becomes our final output. In terms of complexity, the time complexity is O(n), since we visit each node exactly once. The space complexity is O(h), where h is the height of the tree, because the recursion stack can go as deep as the tree's height. For a balanced tree, this height is O log n, but for a skewed tree, it could be O(n). Finally, let's consider some edge cases. For an empty tree, where the root is null, the result will simply be an empty list. In a single node tree, the result will just be a list with that one node's value. Even for skewed trees, where all nodes are either to the left or right, the algorithm works seamlessly by following the correct traversal order regardless of the tree's shape. This implementation solves the binary tree inorder traversal problem using recursion. First, we define a tree node class to represent each node in the binary tree, with attributes for the node's value, val, left child, left, and right child, right. Next, we define the solution class that contains the Inorder Traversal method. The Inorder Traversal method takes the root node of the binary tree as input and returns a list of node values in inorder sequence. We initialize an empty list result to store the traversal order. Inside the method, we define a helper function traverse that performs a recursive traversal of the tree. The base case checks if the current node is null. If it is, we return immediately. Otherwise, we recursively call traverse on the left child, node.left, add the current node's value, node.val, to the result list, and then recursively call traverse on the right child, node.right. Finally, we invoke the traverse function with the root node and return the result list containing the inorder traversal of the tree. This approach ensures all nodes are visited in the correct left root right order. The algorithm runs in O(n) time, where n is the number of nodes, as each node is visited exactly once. Here, we start by defining the basic structure for a binary tree node. The tree node class contains three fields, val to store the value of the node, and left and right to represent its left and right child nodes, respectively. We provide three constructors, a default one that initializes just the value, and another that initializes the value along with the left and right children. After defining the tree node, we move on to the solution class, which contains the method Inorder Traversal. This method takes the root of the tree as input and returns a list of integers representing the inorder traversal of the tree. To achieve this, we create an empty list named result to store the traversal and call a helper method named traverse, passing the root node and the result list as arguments. The traverse method is a recursive helper function that performs the actual inorder traversal. First, it checks if the current node is null. If so, it simply returns, as there's nothing to process. Otherwise, it recursively traverses the left subtree by calling itself with the left child of the current node. Once the left subtree is processed, it adds the value of the current node to the result list, representing the visit step in the inorder traversal. Finally, it recursively traverses the right subtree by calling itself with the right child of the current node. This recursive approach ensures that the nodes are visited in the correct left root right order, and the result list is updated accordingly. To begin, let's consider example 1, which involves a simple tree. The input tree has three nodes, with the root node being 1, its right child being 2, and node 2's left child being 3. We initialize an empty list called result to store the traversal order. Starting at the root node, which is 1, we attempt to traverse its left subtree first. Since node 1 has no left child, the recursive call to traverse its left subtree returns immediately. At this point, we visit node 1 itself and append its value to the result list, giving us result equals 1. Next, we move to the right child of node 1, which is node 2, and recursively call the traversal function. At node 2, we again start by traversing its left subtree, which takes us to node 3. Node 3 has no left child, so the recursive call returns immediately. We then visit node 3 and append its value to the result list, updating it to result equals 1, 3. Finally, since node 3 has no right child, the recursive call to traverse its right subtree also returns immediately. Now we return to node 2. After completing the traversal of its left subtree, we visit node 2 itself and append its value to the result list, making it result equals 1, 3, 2. As node 2 does not have a right child, the recursive call to traverse its right subtree returns immediately. With this, the traversal for the entire tree is complete, and we return to the root node. The final result of the inorder traversal for this tree is 1, 3, 2. Moving on to example 2, we now have a full binary tree with 7 nodes. The root is node 4, which has left and right children 2 and 6, respectively. Each of these children also has 2 children of their own. We start again by initializing an empty result list. At the root node, 4, the first step is to traverse its left subtree, which leads us to node 2. At node 2, we repeat the process and traverse its left subtree, arriving at node 1. Node 1, being a leaf node, does not have a left child. We visit node 1 and append its value to the result list, making it result equals 1. Since node 1 also has no right child, we return to its parent node, 2. At node 2, we now visit it and append its value to the result list, updating it to result equals 1, 2. Next, we traverse the right subtree of node 2, which takes us to node 3. Node 3 also lacks a left child, so we visit it and append its value to the result list, giving us result equals 1, 2, 3. With no right child, we return to the root node, 4. At this point, we visit node 4 and append its value to the result list, making it result equals 1, 2, 3, 4. We then proceed to traverse the right subtree of node 4, reaching node 6. At node 6, we start by traversing its left subtree, arriving at node 5. Node 5 has no left child, so we visit it and append its value to the result list, updating it to result equals 1, 2, 3, 4, 5. With no right child, we return to node 6. At node 6, we visit it and append its value to the result list, making it result equals 1, 2, 3, 4, 5, 6. Next, we traverse the right subtree of node 6, which takes us to node 7. Being a leaf node, node 7 has no left child, so we visit it and append its value to the result list, resulting in result equals 1, 2, 3, 4, 5, 6, 7. Since node 7 also has no right child, the traversal of this tree is complete, and the final result is 1, 2, 3, 4, 5, 6, 7. Finally, let's look at example 3, which involves a single node tree. The only node in the tree is 42. We initialize an empty result list and start at the root node, which is 42. Since it has no left child, the recursive call to traverse its left subtree returns immediately. We then visit node 42 and append its value to the result list, giving us result equals 42. With no right child, the traversal is complete, and the final result for this tree is 42. To analyze the time complexity of the given Inorder traversal, we start by understanding how the recursive function traverse operates. For each node in the binary tree, the function makes one recursive call to the left subtree, processes the node itself by appending its value to the result list, and then makes one recursive call to the right subtree. This means that every node in the tree contributes a constant amount of work, O1, during its visitation. When you consider the entire tree with n nodes, the function is called exactly once for each node, resulting in a total time complexity of O(n). This analysis holds true regardless of the tree structure, whether it's balanced, skewed, or somewhere in between, because every node is visited exactly once, ensuring a time complexity of O(n) in the best, average, and worst cases. Now, turning to the space complexity, there are two main contributors to consider: the result list and the call stack. The result list stores the values of all n nodes in the binary tree, which requires O(n) space. The call stack usage, however, depends on the tree's height. In the worst-case scenario, such as a completely skewed tree, the recursion depth reaches n, leading to an additional O(n) space requirement. In the best-case scenario, for a balanced binary tree, the height of the tree is proportional to log n, so the call stack space is reduced to O log n. When we combine these two factors, the overall space complexity remains O(n) in the worst case, as the result list dominates, and in the best case, it becomes O(n) for the result list plus O log n for the call stack. Comparing this approach to others, a naive or brute force method might involve repeatedly traversing subtrees to reconstruct the Inorder sequence, which would result in redundant operations and a time complexity greater than O(n). Alternatively, an iterative approach using an explicit stack can achieve the same time complexity of O(n), but its space complexity would also be O(n), as the stack is required to simulate the recursion. Finally, the O(n) time complexity of the recursive solution is derived from the fact that each node is visited exactly once, with O(1) work done per node, which aligns with the mathematical definition of big O. Similarly, the space complexity of O(n) is due to the combined storage requirements of the result list and the recursion depth. Overall, the recursive Inorder traversal is optimal in terms of both time and space for solving this problem. When working on binary tree problems, there are several common mistakes to watch out for. One frequent issue is not handling null nodes properly. If you forget to check whether the root is null, your code might throw runtime errors when the tree is empty. The solution is simple: always include a condition to check if the node is null before proceeding with traversal. Another common pitfall arises in recursive solutions, where the base case is either missing or incorrectly defined. Without a proper base case, your function could end up in infinite recursion. To prevent this, make sure the base case stops the recursion when a null node is encountered. In iterative approaches, improper management of the stack can lead to incorrect traversals. For instance, failing to push and pop nodes in the right order might cause you to visit nodes out of sequence. Always ensure you fully traverse the left subtree by pushing nodes onto the stack before starting to pop and visit them. Lastly, modifying the tree structure during traversal, like accidentally changing pointers, can corrupt the tree. Instead, use a separate data structure, such as a stack, to manage the traversal state without altering the original tree structure. Another mistake to avoid is ignoring edge cases. These include scenarios like single-node trees or trees with only left or right subtrees. Testing your solution against a variety of edge cases ensures that it works correctly under all conditions. Shifting focus to interview scenarios, binary tree traversals like inorder, preorder, and postorder are foundational topics. They often appear as part of more complex problems, such as constructing trees or finding the lowest common ancestor. A key discussion point is the trade-off between recursive and iterative solutions. Recursion is often simpler and more intuitive to write, but it risks stack overflow with deep trees. Iteration, on the other hand, uses an explicit stack, offering more control over memory, though it's slightly more complex to implement. Space complexity is another important aspect to highlight. Recursive approaches consume O(h) stack space, where h is the height of the tree, while iterative solutions also require O(h) space for the explicit stack. Be ready to address follow-up variations, such as modifying the traversal to return sorted values for binary search trees or reversing the traversal order for specific use cases. Binary tree traversal problems are closely related to several other LeetCode challenges. For example, binary tree preorder traversal, postorder traversal, and validating binary search trees are all directly related. Additionally, problems like finding the kth smallest element in a binary search tree require a solid understanding of Inorder Traversal since it naturally produces sorted values in a BST. Beyond these, it's also worth exploring alternative approaches and comparing their trade-offs. One such alternative is Morris Traversal, which uses O(1) space by temporarily modifying the tree structure. While this approach eliminates the need for additional memory, it comes with the downside of altering the tree during traversal, which can be problematic if the tree's original structure needs to be preserved. Another option is the recursive approach, which is elegant and concise but risks stack overflow in deeply nested trees, making it less reliable for very large inputs. The iterative approach is another popular method for binary tree traversals. Its main advantage lies in avoiding the limitations of recursion by using an explicit stack. This makes it more robust for handling deep trees without risking stack overflow. However, the trade-off is that the iterative method is slightly more complex to implement compared to recursion. You need to carefully manage the stack to ensure nodes are pushed and popped in the correct order to maintain the proper traversal sequence. By understanding these approaches and their trade-offs, you can select the most effective solution for a given problem while being prepared to discuss the reasoning behind your choice during interviews. Great job following through. We've successfully covered the binary tree Inorder traversal problem, learned both recursive and iterative approaches, and analyzed their complexities. Remember, tree traversal is a foundational skill for many coding interviews. Stay curious, keep practicing, and I'll see you in the next session. Thanks for watching. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!